Zoe Kuhn, and this problem is from Chapter 19 on electrochemistry. Specifically, this problem will involve balancing redox reactions in acidic conditions. The problem we will be addressing is MnO4- plus aluminum solid being reduced to manganese 2+ plus aluminum 3+. The major goals when solving this problem are to balance the redox reaction in an acidic environment, meaning that there will be hydrogen plus ions in the final reaction. To do this, the problem will be broken down into 7 smaller steps, starting with breaking the reaction into 2 half reactions, identifying oxidation numbers throughout the steps, identifying which reaction is being oxidized and which is being reduced, and in turn identifying the cathode and anode of the problem. Step 1 is writing the full unbalanced equation and finding the oxidation numbers of each element in the reaction. Starting with aluminum solid, we know that this has an oxidation number of 0 because that is its neutral state and no charge is indicated with a plus or a minus sign. Manganese 2+ and aluminum 3+ are also easy to determine because the oxidation numbers are given. These are 2+ and 3+ respectively. The MnO4- is a little bit more difficult. We know that oxygen always has an oxidation number of 2-, and we know that the entire compound has to have a -1 charge. Thus, we set up the equation x plus -2 times 4, because there are 4 oxygen atoms, equals -1. After quick algebra to solve for x, we can determine that the oxidation number of manganese is 7+. Now that we have the oxidation numbers of all the elements in the reaction, we can separate the total reaction into 2 half reactions. We take the aluminum ions and pull those apart to make the first half reaction, just aluminum solid to aluminum 3+. Since this reaction is going from a 0 oxidation number to a +3 oxidation number, it is being oxidized. Since it is being oxidized, we automatically know that it is the anode of the problem. We then do the same thing for the manganese ion, but this time, since we are going from a +7 charge on the manganese to a +2 charge, we know that this is being reduced. This automatically makes this the cathode as well. Once we have separated the half reactions, we can begin step 3, which requires us to balance the number of atoms. We balance the atoms and do not pay any attention to the charges on the ions. Since the first reaction is technically just 1 solid aluminum atom to 1 aluminum atom in an aqueous solution, it is already balanced 1-to-1. The second reaction requires us to balance the oxygen atoms in the product side. Since oxygen is in the reactant side with the manganese, but there's no oxygen in the product side, we had to add 4 oxygen atoms to the product side. However, since the reaction is an acidic environment, we couldn't just balance the oxygens by themselves and instead needed to use water atoms. To balance the oxygen, we used 4 water molecules to the product side. However, this then introduced 8 hydrogen atoms to the product side that are not on the reactant side. Because this is an acidic condition, adding hydrogen atoms is a good thing and will not affect the solution overall very much. Our new balanced equations are aluminum solid being oxidized to aluminum 3+, and MnO4- plus 8 hydrogen atoms being reduced to manganese 2+ and 4 water atoms. Step 4 is balancing the charges by adding electrons. Looking at the first reaction, we see that there is a 0 charge on the reactant side and a +3 charge on the product side. To balance this, we have to add 3 negative electrons to the product side, making the new equation aluminum solid being oxidized to aluminum 3+ plus 3 electrons. For the second reaction, we know that the MnO4- compound has a -1 charge, and the 8 hydrogen atoms have a +8 charge, meaning that the reactants together have a +7 charge. The products, on the other hand, has a +2 charge from the manganese ion and a net 0 charge from the water, since water molecules are always 0. Thus, we have +7 on one side and +2 on the other. We have to add 5 negative electrons to the reactant side, so that -5 plus +7 equals +2, which is equal to the charge of the products. Now we have 3 electrons on the product side, in the first equation, and 5 electrons on the reactant side of the second equation. Step 5 involves multiplying the half reactions in order to get an equal number of electrons. Since the first reaction has 3 electrons, and the second reaction has 5 electrons, and the closest common denominator is 15, we have to multiply the entire first reaction by 5, and the entire second reaction by 3. Make sure to multiply every species involved in the reaction. This is the result of multiplying by 5 and 3 respectively for both sides. There are now 15 electrons for both reactions on opposite sides of the arrow, so that they can be cancelled out in the next step. You can also see that everything in the reaction was multiplied by 5 or 3. In the second to last step, cancel all similar terms. The only similar term in both reactions that are on opposite sides of the arrow are the 15 electrons, so those get cancelled out. Everything else is kept. The final step is to just combine everything from the 2 half reactions to get one final reaction. The final reaction is 3 MnO4- plus 24 hydrogen atoms plus 5 aluminum ions redoxing to 3 manganese ions plus 12 water molecules plus 5 aluminum 3+ ions, with the manganese being reduced and the aluminum being oxidized. The highlights of this problem. We were asked to balance the reaction. Over the course of this video, we had to find oxidation numbers either by the values given, such as the case for Mn2+, or through algebra, like with MnO4-. We then had to separate into the half reactions and balance first the number of atoms on both sides of the arrow, then the charges of everything. For both half reactions, there needed to be an equal number of everything on the reactant and product side. Then we balanced the number of electrons and multiplied so that both half reactions had the same amount. We canceled the like terms and created the final reaction with the new charges and balanced atoms. Thank you, and I hope this helped.